Hello and welcome everyone to this new video in our series about OpenGl ES. This is video number 10, and in this video I will be adding a skybox to our scene. However, before I start doing that, I want to change the way we did the camera rotations. Namely, I will be using the lookAt function, as we will see later. Then I will add a skybox to our scene. This skybox will be, as the name suggests, a rectangle which surrounds our all objects. So usually it will be rendered behind the objects. For this skybox, I will be using a feature from OpenGl called cubemaps. This is a type of textures which consists of 6 images instead of 1 image. And you can imagine that these 6 images are surrounding a box as shown here. So you will have one image for the front face, one for the back face, one for the top, one for the bottom, and left and right. The benefits of this cube maps is the direction sampling. So you will see how we will do that in our vertex and fragment shaders. To generate cube maps, you can use software such as Panorama to Cubes. This software is available at this links, and the credit goes to Lucas Crane for making it available. So this is the website. In this application, you can upload a 360 image, and then you can use this small web application to output 6 images, which you can click on and save and use them in OpenGL, as I will show later. Let's start coding. So let us first go to the camera class, which we saved here in the core, and use the new function I prepared. So as you can see, I called this function rotate by, and this function will take 2 angles, X and Y, and we will be also using 2 new member variables called orientation and the up direction. These 2 variables both represents a vector in the 3D coordinate systems. The first vector up, as you can see, it's fixed and it's 0 on the X, 1 on the Y, 0 on the Z, because our up vector is the Y axis. The orientation vector will tell us the direction which we are looking at. I will add 2 other variables, one called default position and one called default orientation, and will initialize them. So the default position, I will set it to 10 on the Z axis, while the default orientation will be looking at the minus direction of the Z axis. These 2 variables I will be using to reset our orientation and camera position. Now we don't need these 2 camera angles, and of course the camera position, we don't need to set it anymore here. We will always set it using the default position. So on the constructor, we create the view matrix and the projection matrix. Then let us call the function reset camera, and that's it. In the reset camera, we will use this in default position and default orientation. So we'll make copies from those and assign them to the camera position and camera orientation. Let me refactor this variable. Now in the scroll, we also need to do some changes. So for the moving and up and down, nothing will be changed. However, since we don't have this cam X and Y angles, we need to define here local variables. I will call them the same name, cam X angle and cam Y angle, and we'll assign 0 to both of them. And we need here also to change the sign. So now if we are rotating, this camera X and Y variables will be assigned some value. And note, since they here start actually by 0, we can directly assign to them minus 30 times the scale and so on here. And now instead of using this translate and rotate, we only now need to call this new function which we have, rotate by. So yeah, actually the name rotate by maybe not the best name because it does both the rotation and the translation. So I will just call it update view matrix. And now in the update view matrix function, the first step is that we take the cross product of the orientation vector with the up direction. So now we get a vector which is perpendicular to both. And if we rotate it around this vector, then we will be rotating the camera up or down. That's why you can see here that we are rotating the vector orientation with the angle X around the vector cross to get a new orientation. Then we compute the angle between the new orientation and the up vector, and we want this angle to be smaller than 90 degrees basically, so we don't want to flip our view, and that happens when our angle is plus 90 or minus 90. So if the angle is in this range, then we assign the new orientation to the current orientation, and then we rotate around the up direction, so that's like looking around left or right if you like. The resulting orientation, we will add it to the camera position, and that would be the new position where we are looking at. Then we can use this function from the matrix class called lookAt. This function takes the matrix which we want to update, and then the camera position, then the location which we are looking at, and finally the up direction. And then it will use this information here to update the matrix, and that's it for this update view matrix. And I noticed that I used now this minus sign everywhere, which is very confusing, so let me remove them. And now let's test our code. It seems that the X and Y direction is reversed here. However, the rotation is working correctly, so what I need to do is to change these two signs here and this one. And now we move towards the sphere, away from the sphere, to the left, to the right, and the same up and down, and of course the rotation. And if everything is mixed, we reset the view. And that's it for the camera changes. Let's go to the skybox. So I already prepared the class skybox. Let me paste this class here inside custom objects. And for the skybox, we need these new vertex and fragment shaders. I also prepared those. Let me copy them. So let's go through this class. As you can see, this skybox extends the abstract object class. So as before, it contains a program, vertices, and vertex buffer. We also here keep the number of vertices and the stride. Since we will have now 6 textures, we need a string array which will hold the name of the images which we will be using in this texture, and a variable to hold the texture. We will also need now to change the texture class to accept 6 images and make a cube map from them. We will look into that later. But for now, let's go to the constructor. In the constructor, we need the scale that tell us how big this cube should be, and the images which we will be using for this skybox. So we have right, left, top, bottom, front, and back. So the first step in this constructor is that we create the vertices of a cube using the cubevert class, which we created in a previous tutorial. Then we set the strides to be the number of floats per positions, since we already will be using X, Y, and Z. And the number of vertices would be now the length of this array divided by 3. And then we initialize our textures with the paths we got as an input to this constructor. So in the function on init, we first need to load our program, which we already created, and then create the vertex buffer and load the vertices to that buffer, and then use our program, then initialize the attributes. We will be using only a position attribute here, as you can see. So that's why the stride is only 3 floats, and the current offset will be here 0. Then we need to load the texture, which we will look at in a minute. The onUpdate and onDestroy are empty as before. The draw function is very similar to the previous objects which we have created. So we use the program, we bind the buffer and the texture, then we set the uniforms, the model, view, and projection matrices, and then draw the triangles. However, as you can see, we have here an extra call to a function called setTips function, L=, and then here setTips function to less. Let's have a look at this function. I will put them into the A object class. As you can see, these two calls are very simple. So the first one calls the function glTips function with the parameter less or equal, while the second one uses the default dips, which is less. So the idea here is that we will make sure in the shaders that we always get the dips to be 1, and that's why we'll be using less or equal, so that our skybox will be always rendered, and then we switch back to the default function. Let's have a look now to the vertex and fragment shaders. So the vertex shader is as before. We have an attribute, call it a position. We have an output, a vector3, which is the texture. As we said, we will be using 3D sampler here. Then we will have these three uniforms as before. So for each vertex, we'll start first by computing this variable position as before, which is the position multiplied by the model view projection matrix. Then we will set our GL position to be the X, Y, and then we will use the W for the Z and the same W here. Now when this vector is normalized by the W, by the fourth coordinate, the Z coordinate will always be 1. And that's what we want. And now for the texture, we will be using the vector which is pointing from the center, so from the origin 0, 0, 0 to the current point. And for that, we take the X and Y and the negative Z here, and we normalize this vector. So now we got a direction vector, and that will be used as our output texture. The flip on the Z direction is done because in the texture, a left-hand coordinate system is used and not the right one. That's why we need to flip the Z direction. Now in the fragment shader is also similar to the previous ones, except that now we are using a sampler cube. We called it skybox. And now in the texture, we use this cube sampler with our vector3, this directional vector, and that will give us our color. That's it for the fragment shader. So now the only thing is missing is to load our texture, and for that let's start with the class texture. So in this class we have to do some changes because now we want this class to be handling not only simple texture but also cube texture. So I first will add a boolean variable called isCube. It will be false by default, and then of course we have this function load for the normal texture. For this we will put also the value isCube to false, and then we will add another load function to load a cube texture, and this function will take now an array of strings and it will put this isCube to true and calls a function called send cube texture to GL. Let me put this function here below send texture to GL. As you can see, this function is very similar to the previous one. It starts by generating a buffer and saving the ID to be used later, then binding these buffers, then setting the filter parameter to the cube map. So we want to have linear filtering, and then also for the coordinates we want to use clump to edge to prevent some artifacts from appearing in our scene. And then we start loading the bitmaps. So as you can see, we loop over the strings which we will have in the input, which should be 6 strings. Each time we load the bitmap and then we send it to the OpenGL. So this is the position of the bitmap in the buffer, and then we recycle the bitmap. So very much similar to the previous one, except now we do it like 6 times, and that's it. So now the bind function needs a small change. So if we are in the cube, we need to bind cubemap. If not, we will be binding a texture 2D as before. And that's it. Let's go now and use our skybox. So I will put the code here before the sphere. So as you can see, we are loading the skybox. We are putting the scale to be very large, 300. So that will contain all our scene. And of course, we need the images. And then we just add this skybox to the scene as before. And now we need to add those images into this path. So let me paste them here. And as you can see, now we have these 6 images. Now let's test. Now we forgot to add this function to the scene. Let's do that. So I will put it here after this function load texture. So we'll add this load cube texture, which is very similar to the previous one. So it looks, if the texture exists, then it return it, else it create a texture and load it, and then return the new created texture. So let's run. So now as you can see, we are inside this cube. We can go towards the cube or away from the back face. We can rotate down. So now we are looking down. Let's rotate again down. Now in the other direction. So you can always come to the default view. And let's do a full rotation. Now let's move up rotate up, back down. And that's it for this video. Thank you for watching. Please give me a thumb up if you like the video and subscribe the channel so I can do more videos. And see you in the next video. Bye.